Swayam Prabha. Digital India. Educated India.
Welcome to the course on advanced machining processes. Today I am going to discuss about electric discharge grinding. Sometimes it is also called as electric discharge diamond grinding. Organization is like this. I am going to talk about the introduction, where I will talk general grinding and electric discharge grinding, or electric discharge abrasive grinding and electric discharge diamond grinding. Then some details of experimental setup, some results of experiments, and then conclusions. Now, a lot of technological developments are taking place in different fields, especially the materials. A large amount of research is going on across the globe in the area of material science and materials engineering. Every day materials are being developed according to the requirements. They also call it a engineered materials, where you can have the properties of the material as per your requirements. They have many times very hard materials, high strength, high temperature resistant, and to shape and size these materials really becomes a challenge for a manufacturing engineers. And when you want to shape and size these materials components, somewhere or other you have to perform machining operations on these materials, as well as sometimes finishing operations on these materials. And these materials are so hard that conventional cutting tools cannot machine these materials, because these materials are either equal to the hardness of the conventional cutting tools or more than conventional cutting tools. So, many materials are designed and engineered such that they can be machined and finished by the unconventional machining processes, especially EDM or electric discharge grinding or electric discharge diamond grinding. Cutting tool industries deal with carbide, cutting tungsten carbide and other kind of the carbide tools, cermets which has ceramics as well as metal components, and PCD polycrystalline diamond cutting tools are made. Process involved, you many times perform the operation known as diamond grinding, where the abrasive wheel is having diamond particles as the abrasive, or the grinding wheel is having the bonding material and the diamond as the abrasive particles for performing the grinding operations. Now, there is another process known as electric discharge machining. Now, in case of electric discharge machining, you can shape and size the components, but the material removal rate is very small. And in case of diamond grinding, surface finish is good, but wear and tear of the grinding wheel keeps taking place. These grinding wheels are very expensive. Moreover, both these processes are thermal processes, so thermal cracks are developed in the finished component or machine component. With diamond grinding, which is quite common in various types of high tech industries, there are certain limitations, because of which this process has limited applications. First thing is, diamond grinding initial equipment itself is very expensive and the cost of the grinding wheel is also quite high. Then high specific material removal energy requirement is there. That means, the energy requirement per unit volume of material removal is much higher compared to other machining processes. As a result of high amount of heat generation on the workpiece as well as on the grinding wheel, there is a degradation of the strength of the workpiece takes place. Mainly the micro cracks may develop, thermal residual stresses in the finished component or machine components are observed, and due to the wheel wear, dressing becomes really problem. As per conventional dressing of the grinding wheel, a large amount of abrasive particles or diamond particles are lost, and diamond grinding becomes quite expensive and low productivity process. EDM process, electric discharge machining process, about which we have already discussed quite a bit. Now, this process gives very low material removal rate and the material removal efficiency is also low. That means, the energy required per unit volume of material removed is quite high. After EDM process, you get a resolidified layer, that is known as white layer or recast layer on the machine component, and this recast layer is very hard. It may be 2 to 3 times harder than the base material or the parent material of the workpiece, and it has micro cracks. So, after EDM process, the component cannot be used as such in the sub assembly or assembly. It has to be subjected such that this recast layer, resolidified layer or white layer is removed, and that requires additional time, one more operation, and it costs something to the component. That is why a new grinding processes or hybrid grinding processes are being developed. Some of them are like electric discharge, abrasive grinding or diamond grinding, electrochemical grinding and other processes. We are today going to discuss about the electric discharge grinding, electric discharge abrasive grinding and electric discharge diamond grinding. Now, grinding of hard materials requires high force, high normal force, because normal force is responsible for penetration of the abrasive particles into the workpiece surface, and shear force is responsible for the removal of the material in the form of the micro nano chips, and then rapid formation of wear flat. When you are doing the grinding operation, then the abrasive particles which are projecting out of the grinding wheel, they wear and wear flat is created. As a result of that, grinding efficiency goes down. Wheel clogging is a common practice, or rather a common event that take place during grinding process. As you can see here, that say this is the wheel and there are the abrasive particles on the wheel. Then what happens when you are performing the grinding operation, then between the abrasive particle the chips get locked up, and as a result of this the sharpness of the grinding wheel which is in contact with the workpiece reduces, and because of this clogging of the grinding wheel, the machining efficiency or the grinding efficiency goes down. Force required become much larger than really anticipated. Hence, to overcome this problem, you have to go for what is known as dressing of the grinding wheel, so that these locked material is removed and some of these abrasive particles are plugged out of the grinding wheel even without being used. So, there is a additional loss of the abrasive particles during the dressing, which is really not needed, hence it makes inefficient mechanical dressing process. Now, since the materials are very hard which we are intending to grind, it requires very high normal force and definitely large shear force also. The solution for this can be that somehow if we can soften these very hard workpiece material, then the normal force required as well as shear force required, both of them will reduce. Hence, we will see how to do the thermal softening of the workpiece during the grinding operation. If thermal softening is taking place, there will be the reduction in the shear as well as the normal forces. You can achieve better accuracy on the finished component, better surface integrity, because once the material is soft and you are removing the material, then definitely the probability of the micro cracks and thermal residual stresses goes down. Now, here in case of electric discharge abrasive grinding as well as electric discharge diamond grinding, I will show you in the following slides that in process dressing takes place without performing any additional dressing operation manually. This in process dressing is more efficient than mechanical dressing, which I explained you. There is no loss of machining time, that means you are not stopping the grinding operation and then performing the dressing operation, which is normally done in case of conventional grinding or even diamond grinding. Here it is a part of the process itself, that is electric discharge diamond grinding or electric discharge abrasive grinding, that during grinding operation itself dressing keeps taking place and selective declogging is also going on. No sliding contact between bond and workpiece. Now, since continuous dressing and declogging of the grinding wheel are taking place, so abrasive particles and only abrasive particles are always in contact with the workpiece. As a result of that, no sliding contact takes place between the bond material and the workpiece material. Now, here one point is very important to note. Here bonding material should be metallic, it should be electrically conducting, otherwise it will not work in electric discharge abrasive grinding or electric discharge diamond grinding, because we have already seen that in EDM the cutting tool acts as a cathode, workpiece acts as the anode. Now, in electric discharge diamond grinding also the grinding wheel is acting as the cathode and workpiece is acting as the anode. Now, if wheel is to act as the cathode, then definitely it should be electrically conducting material. Composition or rather comparison with electrochemical grinding, there is another process, hybrid process, which is known as electrochemical grinding. Now, in case of electrochemical grinding, as we will see, lot of sludge problem is there, sludge formation is taking place because of electrochemical reaction in the electrolytic cell, as we have seen in case of electrochemical machining, that ferrous hydroxide and ferric hydroxide are formed when you are doing electrochemical machining. Same way, when you are doing electrochemical grinding of say ferrous materials, then ferrous hydroxide and ferric hydroxide, that is the sludge, are formed, and the disposal of these sludge becomes a problem. They block many times the inter-electrode gap, and short circuit probability is much higher in case of electrochemical grinding compared to electrochemical machining. But in case of electric discharge diamond grinding or electric discharge abrasive grinding, no such sludge formation is there. So, short circuit probability is minimal. Now, material removal mostly due to abrasion is taking place in general grinding, but in electrochemical grinding this is not really very true that most of the material removal is taking place due to the abrasive action. No, in this case, in case of electrochemical grinding, about 10% of material removal takes place due to the abrasive action, while 90% takes place due to the electrochemical dissolution. Let us see electric discharge diamond grinding. Now, here two words are there, one is electric discharge, second is the grinding, and electric discharge diamond is used as the abrasive particle on the grinding wheel. So, it is called as electric discharge diamond grinding. I have already mentioned some details about the electrochemical grinding. This is again a hybrid process, very useful process. Then you have electrochemical arc machining. This particular process is another hybrid process where ECM and EDM both are combined together to take the advantage of ECM process as well as EDM process, because ECM process has very high material removal rate while EDM process has very low material removal rate. EDM creates a problem of surface integrity, especially of micro cracks, while ECM does not do so. So, by combining these two processes, the unique feature of this ECSM or electrochemical arc machining is that it combines the two and material removal rate goes much higher than ECM or EDM, and it becomes the combination of ECM as well as EDM process. Then there is another very interesting process known as electrochemical spark machining process, where ECM and EDM again both are combined, but in this particular process it is basically used for electrically non-conducting materials like ceramic materials, while electrochemical arc machining is used for electrically conducting material. So, there is a big difference, although in case of ECSM, ECM is used for electrically conducting material, EDM is used for electrically conducting material, but the beauty of this ECSM process or electrochemical spark machining process is that it is used for electrically non-conducting material. Then there is a hybrid process where EDM process is taking the help of ultrasonic vibration and combining ultrasonic machining and EDM process, and you can call it as ultrasonic assisted EDM process. Then there is a plasma jet laser beam assisted machining process, again a hybrid process is there. So, these are the general hybrid processes for machining. Same way, grinding process can also be classified into two categories: conventional grinding and hybrid grinding. Hybrid grinding I have already mentioned to you, ultrasonic assisted abrasive grinding, electrochemical grinding which I have already discussed, electric discharge abrasive grinding, electric discharge diamond grinding, etc. There are various other processes. Now, electric discharge diamond grinding, as I have mentioned, that diamond diamond particles are used as the abrasive particles. Now, there was another process in the earlier slide, I called it as EDAG, electric discharge abrasive grinding. Here, in place of diamond particles, other abrasive particles are used, just like alumina Al2O3 or tungsten silicon carbide SiC or CBN cubic boron nitride particles, they can be used as the abrasive particle, then you call it as electric discharge abrasive grinding. Now, again here grinding operation is coupled with the EDM operation. Now, since EDM requires electrically conducting cathode, so bonding material in the grinding wheel is electrically conducting material. This is using metal bonded grinding wheel. So, workpiece material also has to be electrically conducting, because this EDM process is applicable only for electrically conducting materials. In process, continuous dressing and declogging is the main feature of this particular process, which I have already mentioned. Now, because of in process continuous dressing and declogging, all the time abrasive particles, sharp abrasive particles are in contact with the workpiece surface during grinding operation. That is why grinding force is reduced. This gives a clear picture of the rotating disc electrode for EDM process. I will explain it. Now, here you can call it as electric discharge grinding. Please note it carefully, I am calling it electric discharge grinding rather than electric discharge abrasive grinding or electric discharge diamond grinding. What is being done here is, you can see here is a rotating disc which is rotating just like a grinding wheel, and this setup has been connected to the NC EDM machine. Now, the main thing here is that this is the disc which is not having any abrasive particle, neither alumina nor silicon carbide or diamond particles, because this disc is rotating and then removing the material. Here is the workpiece as you can see. So, they people call it as electric discharge grinding. In real sense, it is really not a grinding operation, because abrasive particles are not being used, only for slicing purposes or machining flat surfaces etc. This process can be used. Here you can see the inter electrode gap is controlled by the servo system, and RAM is there, and servo system is already there, rotating disc is there, dielectric, it is partially dipped in the dielectric, and normally kerosene is used as the dielectric, and here is the workpiece which is connected to the positive terminal of the power source. So, it is really simply a EDM process, but called as electric discharge grinding because the because the disc is rotating. Here no abrasive particles are used, only rotation of the disc type electrode is there, hence it is called as the electric discharge grinding. This has been taken from the paper as referred over here, which was published in Machine to Precision Engineering Journal. Now, let us see the experimental setup for electric discharge diamond grinding. Now, here you can see all the features of the electric discharge diamond grinding process are shown over there. Let us see them clearly. Now, here is the CNC EDM pulse power generator and the grinding wheel. This is the grinding wheel, diamond grinding wheel, which is connected to the negative terminal of the pulse power supply generator, and the nature of the pulse you can see here. This is the voltage pulse which is having on time and off time. This is the on time over there, and this is the off time of the power pulse power supply, and this is connected to the computer or PC, from where you can control the different features, that is the on time and the duty cycle can be controlled with the help of the computer, and it is interfaced with the servo control system over there. Now, this is the tank is filled with the dielectric. You can use kerosene, paraffin oil or some other oil as the dielectric, but mostly it is the kerosene which is used as the dielectric. Now, let us see what is happening as long as supply of dielectric is concerned. This dielectric comes from the tank, from this machining zone or machining tank or machining pot, whatever you want to call, and it comes to the tank where filtration takes place, so that the debris etc. are removed, and after proper filtration you supply it to the pump, and then it is further filtered at the second stage, so that any unwanted debris or solid particles are removed, very fine solid particles are also removed here, and then it is supplied to the machining area tank. Dielectric fluid is there. Now, in this zone, if you see clearly where abrasive particle is there, the enlarged view of this particular zone is here. You can see this is the abrasive particle, this is the metal bond, and it is acting as the cathode. It is connected to the negative terminal as you can see, and the workpiece is connected to the positive terminal. So, it is acting as the anode. Now, sparking is taking place between the grinding wheel and the workpiece. Now, here the point to note is very important. This is the wheel and this is the workpiece, and you can see here the sparking is taking place. So, material is being removed from the grinding wheel as well as more amount of material is removed from the workpiece. Now, point to note here is that material is being removed continuously from the grinding wheel also, and because of this removal of the material, once the abrasive particle does not get sufficient support from the bonding material, it pulls out automatically due to the force being applied on it, and as a result of that both the this dressing of the grinding wheel keeps taking place. Now, here heat is being generated on the grinding wheel, whatever is the clogging of the material, that also gets melted out due to the heat generation between the on the grinding wheel as well as the workpiece. So, from the grinding wheel the material is being melted out continuously, that is why clogging problem does not arise to a large extent, and because the material is being continuously melted out from the grinding wheel, clogging does not take place. That is why I mentioned earlier that in process declogging and dressing of the grinding wheel keeps taking place, and this is a big additional advantage of electric discharge diamond grinding. Here you can see this is the grain projection that is shown over here, and that also is making what is known as inter electrode gap like this over here. Now, another important thing is because abrasive grains are always projecting out whatsoever small it may be in terms of few microns, and they do not allow the bonding material or the grinding wheel to touch the workpiece material and lead to the short circuiting. So, because of these projecting abrasive particles, short circuiting is avoided. Now, the question arises, as I mentioned earlier, that this particular process is good for grinding very hard materials. The reason given was that the process is able to soften the workpiece to reduce the hardness of this or make it soft and then remove the material. Now, this picture gives a clear cut idea how this is happening. Now, sparking is taking place between the metal bond material and the workpiece, and some amount of material is being removed from the tool, but larger amount of material is being removed from the workpiece due to sparking. But more important is large amount of heat is generated over here, and this heat is conducted away in the workpiece, and this heat of spark softens the workpiece, and behind this spark you can see that abrasive particle is coming, and since this material has softened out. So, this abrasive particle will be able to easily remove the softer material as compared to the harder material if spark was not there. So, due to this sparking, it is able to soft the workpiece material, and behind the spark abrasive particle is there which is going to remove the soft material from the workpiece with lower forces, normal as well as tangential, compared to the case when you do not have the spark. This photograph has been taken from this particular paper published in the Precision Engineering. Now, there are basically two configurations of the grinding operation. One configuration you can see here, that one, this is the grinding wheel, maybe diamond grinding wheel, or it may be the other abrasive grinding wheel. Then you have the workpiece over here, and here is the power supply. So, you are rotating this grinding wheel, as due to the rotation of the grinding wheel there is a relative motion between the abrasive particle on the grinding wheel and the workpiece, and this is able to remove the material in the form of the microchip workpiece. Another configuration is like this, that workpiece is electrically non-conducting, and there is a electrode which is electrically conducting, and there is a grinding wheel which is again electrically conducting bonding material, and dummy electrode in the grinding wheel they are connected to the power supply 3 over here, and here is the workpiece which may be electrically conducting, it may be electrically non conducting. Both of them can be machined or ground rather, because there is a relative motion between the workpiece and the grinding wheel, or in other words you can say there is a relative motion between the abrasive particle on the metal bonded grinding wheel and the workpiece, and as a result of that it is able to remove the material or to grind the workpiece. Now, on the back you can see here there is a shaft which is connected to the grinding wheel, and this shaft is connected to the power supply. Brush is there which connects this to supply the or to connect it to the negative terminal of the power supply. So, the grinding wheel setup looks like this, that this is the wheel, metal bonded grinding wheel or diamond wheel which is rotating, and here is the partially the grinding wheel is dipped inside the dielectric, and then it is removing the material from the workpiece, as you can see here in this particular picture. Now, workpiece materials can be very hard, as we have mentioned earlier also. It can be high speed steel, it can be cemented carbide, but all these materials should have a certain minimum electrical conductivity, so that they can be a part of electrical circuit. This I had mentioned to you in the earlier lecture. There are various parameters in this particular process. As you can see, wheel speed is there, current is there, pulse on time is there. I have not mentioned here other parameters like diamond particle size, and then I have also not mentioned the density of the diamond particles on the grinding wheel. To some extent, bonding materials, electrical conductivity or electrical properties will also make a difference in the grinding process, electric discharge diamond grinding process. Also, which dielectric you are using, that will also make the difference, and then what is the voltage or the current what is the voltage you are using in this particular process. The responses that can be measured to evaluate the performance of this electric discharge diamond grinding are material removal rate. This you can give either in terms of volumetric material removal rate or mass material removal rate. Then the normal force that is acting on the grinding wheel, and then there is the tangential force. Now, this normal force is responsible for penetration, tangential force is responsible for removal of the material from the workpiece. So, metal bonded alumina wheels can be more economic than the metal bonded diamond wheels, because the cost of the alumina is much lower than the diamond particles. So, they can be tried upon for various materials as the workpiece. Now, some experiments have been conducted by various researchers to find out or to evaluate the performance of the electric discharge diamond grinding process or electric discharge abrasive grinding process. Now, here you can see the main parameter is wheel speed, that is the RPM of the grinding wheel, and here is the volumetric material removal rate in terms of cubic millimeter per minute. Now, important thing you can see here is that as the current is increasing, the volumetric material removal rate is increasing. Here is the 0 current, that means it becomes a normal grinding operation with the help of diamond wheel. So, you can call it as diamond grinding, where you have the 0 ampere as the current, but as you are increasing the current, the volumetric material removal rate is also increasing. Here is the 1 ampere, 2.5 ampere and 5 ampere. Now, apart from that, formation of wear flats due to the graphitization of diamond takes place, and then you have reduction in material removal rate at higher end of wheel speed due to the wear flat formation, as you can see here. Introduction of current in the spar gap improves material removal rate at all wheel speed, that we have seen that as the wheel speed is increasing, the Yes, another point is, as the wheel speed is increasing, the material removal rate is also increasing. So, with the increase in the current or the wheel speed, material removal rate is increasing continuously, and this is the minimum wheel speed that we use while performing the experiment. So, we have extrapolated this to the material removal rate axis, and you can see that with the even with the 0 current you are able to get certain material removal rate. Now, effect of current on material removal rate, we can see at 0 current in the gap, the material removal rate is very low, while as the current is increasing 1 ampere, 2.5 ampere and 5 ampere, it is continuously increasing. And radial wheel wear is another important parameter which decides the total wheel life, and this should be minimum. So, here you can see, as the current is increasing, the radial wheel wear is also increasing, it is in terms of micrometer per minute. In process dressing is taking place continuously in this particular case. Microstructure of diamond abrasive particle, shifting of critical rake angle towards more negative values takes place during this electric discharge diamond grinding. Now, let us see the effect of current on normal force. Here this picture shows the effect of gap current, inter-electrode gap current on the normal force. Now, as the gap current increases, the normal force is decreasing, not in a linear way, but rather in the non-linear way, as you can see at different speeds of the table, that is 1.5 meter per second, 3 meter per second and 4.5 meter per second. Normal force decreases with the current increase, and we can see at a particular current normal force is higher for higher speed. This is the speed. So, if you take a particular current, as the speed increases, also the normal force is increasing. The reason is very simple, that as speed increases, then the time for the heat to soften the workpiece is low, and if the time for the heat to penetrate inside the workpiece and soften it is low, then definitely its hardness will be more, and if hardness is more, then normal force for penetration of the abrasive particle inside the workpiece will be more. So, that is what is very clear over here, and as the gap current increases, the amount of heat input to the workpiece is more, and if the amount of heat input to the workpiece is more, then definitely its temperature will be higher, and if it has the higher temperature, then workpiece will become softer, and that is why you can see that as the gap current is increasing, the workpiece becomes soft, more and more soft, and the normal force decreases, as you can see over here on any speed. Now, thermal softening effect, higher the current, higher softening, and lower is the normal force, which is very obvious over here, and also higher the speed of the movement of the table or the workpiece with respect to the spark, and higher is the normal force or lower is the softening. Now, let us see here mechanism of material removal in electric discharge diamond grinding. It is very important to know how the material is being removed. Basically, we anticipate the two things to happen simultaneously. One is the abrasive or abrasion of the workpiece material by the abrasive grinding operation or the diamond grinding operation, which is going to produce the chips of irregular shapes depending upon the shape of the abrasive particle. There is a significant role of the EDM process also. Now, how the material is being removed, or what is the mechanism of material removal when both processes are acting simultaneously. So, what we did, we took the micrograph of surface ground at different current, that is 0 ampere, 1 ampere and 5 ampere at wheel speed of 4.5 ampere, and let us see these pictures. Now, if you see the first one where it is A written and 0 ampere, they are clearly visible marks of the grinding operation, and there is hardly any evidence of sparking in this particular first figure. If we see the second one, where 1 ampere current is being supplied in the inter-electrode gap, there are the grinding marks visible, as you can see I have marked over here. But at the same time, if you see carefully, there are some marks of the crater formation, some kind of very close to spherical crater formation. These marks indicate that it is not only grinding, rather some EDM process to some extent is also taking place, and that is very obvious from this second micrograph. Now, if you go for third micrograph, where 5 ampere is current is being supplied between the grinding wheel and the workpiece, there are very minimal 1 or 2 grinding marks clearly visible over there. Otherwise, rest of it is very clearly visible craters of different sizes, as you can see I have marked some of them over here. So, this indicates that major removal of the material at 5 ampere is due to the EDM process. However, grinding is also contributing substantially, but they are not visible because frequency of sparking is quite high, and whatever grinding mark that we see in the first and second micrographs, they become invisible or they get overlapped by the crater formation. So, micrographs not shown here indicated extent of melting decreases with increasing wheel speed. I have not shown those micrographs here, but we observed it. Also, larger force at higher wheel speed, but same current I have already explained in the earlier slide. So, it clearly indicates that both the mechanism grinding or abrasion as well as EDM process are taking place simultaneously in case of electric discharge diamond grinding. Discharge instability at higher wheel speed takes place. So, as wheel speed keeps increasing, the increase in the material removal rate is not linear. That is why it is non-linear, because at higher wheel speed the instability comes into picture. Increased depth of cut due to reduction in gap associated with improved flushing. Now, I also mentioned that wheel loading or clogging over there. Now, we try to take some pictures of the wheel loading, and this is the diamond grinding wheel, here is shown as the scale. Now, you can clearly see these debris between the abrasive particles, and these debris they lead to what is known as wheel loading or clogging of the abrasive particles with the help of the debris. Now, another important point to note in this particular figure is this, which I am showing by the arrows. These are the craters formed, and these craters are formed due to the sparking phenomena taking place between the grinding wheel and the workpiece. You can clearly see many craters that are visible clearly over here in these pictures. So, it also indicates that it is not only the grinding operation, but EDM operation is continuously taking place. Now, you can see here at 0.4 ampere current, which is quite low, grinding marks are quite visible, but there is a decreased contribution of grinding in material removal as current increases. I have shown to you, I will show you again. Now, these are the grinding marks quite visible, but there are at some places you can see the craters also visible over there, that indicate that yes, sparking is also contributing to the material removal over there. Now, at higher current, that is 2.1 ampere, you can clearly see the crater formation, the removal of the material by the craters. Now, if you see this particular point here, it looks like a globule, and this globule or here is there, they indicate that material is being removed by melting phenomena as well, because when material gets melted out and it solidifies, then its shape is spherical, and that is what you can see over here, and they will be more clear in this particular picture. You can clearly see the ball kind of the things or globules kind of the things, which clearly indicate that, and this is at 5 ampere current and 4.5 meter per second speed, that mechanism of material removal is melting as well as grinding melting evidences are very clearly visible over here, and this work has been taken from the paper published by Koshi, Jain and G.K. Lal. Now, declogging of grinding wheel, how does it take place? So, that is what we have tried to model it over here. You can see here, this is the clogged material which has got deposited between the two abrasive particles. There will be another abrasive particle on this side and there will be another abrasive particle on the left side. The gap between the bottom face of the diamond grinding wheel and top face of the workpiece where material is being removed, that is known as inter electrode gap, and this is the height of the clogged material and this is the thickness to which the abrasive particle has penetrated inside the workpiece. And when this is moving in this sparking takes place between this metal as well as the workpiece, and due to that sparking this clogged material gets removed from the grinding wheel as well as some material gets removed from the workpiece as well, and it makes the workpiece soft compared to the parent material hardness. So, material removal by brittle fracture and ductile deformation, it may take place, depends upon the properties of the workpiece material, whether it is brittle or ductile. Wheel loading while grinding cemented carbide has been demonstrated here with the help of a schematic model, and effect of declogging is dislodging of abrasive at a higher current. Now, as this gets dislodged, the clogged material get dislodged, there is a gap between the continuous removal of the material from the grinding wheel also keeps taking place, and once this becomes, this abrasive particles become loosely held by the bonding material due to the force acting in this particular direction as well as normal force acting over here, this gets pulled out of the grinding wheel and continuously fresh abrasive particles are projecting on the grinding wheel and they are removing the material more efficiently rather than worn out material continuously removing the material from the workpiece. So, based on this study certain conclusions have been made. First one is electric discharge diamond grinding is technologically attractive for grinding electrically conducting hard materials. The improved grinding performance due to continuous dressing and declogging is obtained. Optimization of the process is essential for making this particular electric discharge diamond grinding or electric discharge abrasive grinding as economically viable, and it is possible, the possibility of machining hard material with aluminum oxide is feasible, because when the workpiece material is becoming soft, then the aluminum oxide, although not very hard, this can also remove the material for grinding purposes, and advantages of the thermal softening effect due to the sparking can be taken, because aluminum grinding wheels are much cheaper compared to the diamond grinding wheels. Thank you very much.